Hi, can you hear me?
Yes, sir.
Oh. Okay, we'll start. So last time we were discussing complex numbers, and we started to solve some problems using that. Actually, the problem which I picked last time, right? I realized that's not the best starting point. So we will do that problem also, but I think we need to work with some simpler problems first. But before that, I just want to quickly recap the overall points about complex numbers because I missed to mention one or two small things or emphasize the importance of some observations. So I just want to quickly go over the main points about what we discussed last time. I mean, in a way, you can say last time was an informal introduction to complex numbers, but in order to fully discuss the details, we need to add a few other things. So, I mean, roughly speaking, we all know how we define the set of complex numbers. It is the set of all numbers of the type a plus ib, where a and b are real numbers, and I is the special number who has the property I square equal to -1. And as I said last time that there could be multiple symbols like I and minus I which satisfy this property. It doesn't matter which of them you call I. I mean the whole math remains consistent no matter which symbol you call I. And then we define if Z1 and Z2 are two complex numbers, then we define how to add them and things like that. So Z1 plus Z2 was a component wise addition. And the product was basically you expand just the way you expand typical brackets. Okay, and we looked at the geometric interpretations of these two operations. So Z1 plus Z2 is basically in the geometric space. This is like a translation. So when you add a vector v to any given complex number, effectively you are adding a translation of that vector to the whole plane, and the multiplication was a spiral homothéty. So we will revisit these points in more details when we do some examples today. But like broadly speaking, this is where the power of complex numbers comes. That these basic operations can be represented as geometric transformations. And one more which we need to add is the conjugation. So a conjugate of z, which is denoted by z bar, and it is simply the reflection of the z in the x-axis. If z is a plus ib, then z bar is defined as a minus ib. Okay. So in the normal 2D plane representation, basically z is over here, then z bar is over here. Okay. So the same real part, but the imaginary part is reversed. So therefore, I mean, z bar is also does have a mathematical or geometric representation. This is reflection in the line. Okay. And then one more operation, which is basically if you think about what is the meaning of 1 over z. Okay. So 1 over z, if z is some non-zero complex number, then we can write 1 over z also. So I mean, we could do this in the normal Cartesian domain, but as we saw last time, multiplication and the same way division will also be simpler in the polar domain. So for consistency of notation, I think this might be the general way of showing it, but at least for us, we will use this r angle theta notation. So if z is a plus ib, if I want to write the polar coordinates, I'll write it like this: r angle theta. So which means that this z has a magnitude r and argument theta. Okay. And last time we saw how to convert back and forth between the polar version of this equation and the Cartesian version. Uh, so if we represent z in this way, then you can see that 1 by z will be what will be 1 by z in polar domain? So it will be 1 upon r angle minus theta. And the reason for that is basically when we multiply these two together, I'm expecting the answer to be 1. And 1 in the polar domain is simply 1 angle 0, because 1 means basically the magnitude is 1 and the angle is 0 with respect to the x-axis. So for this to happen, when I multiply these two, as we saw last time, the argument gets added. So theta plus minus theta will be 0, and the magnitude gets multiplied. So r into 1 by r equal to 1. So therefore, it makes sense to represent 1 by z as 1 by r angle minus theta. Okay. In the 2D plane, how will we denote this? So for example, if this is my unit vector, so this is my point 1 comma 0. Okay, and let's say z is somewhere over here. Okay, which means this length is r and this angle is theta. Okay, then 1 by z will be somewhere around here probably. Okay, so basically this angle has become minus theta. It has gone to the other direction, and the magnitude is also reversed. And as I mentioned last time about the spiral homothency, basically if you look at these triangles, you'll realize that they are similar triangles. So if I do these names UA and B, then because basically both triangle BOU and triangle UOA have the same SAS configuration, right? Because the magnitude of the adjacent sides, that ratio is the same, because OA, so AO upon OU, OA upon OU will be equal to the magnitude of R, or R, magnitude of Z, and this will be also equal to OU upon OB. So therefore, and the angles in between are of course similar. So basically, these two triangles are similar. Okay, and this will happen in general. Anytime you're multiplying two complex numbers, you'll get similar triangles like this. But in particular, what I want to observe here is that so this B has length 1 by Z, 1 by R. Suppose I take the conjugate of that point. So the conjugate of this point will be somewhere over here. So this point, if I call it B dash, do you realize that OA into OB dash in the geometric sense is basically R into 1 by R, which is equal to 1. so which is equal to OU square. So in other words, if I consider the circle with center O and radius OU, okay, so this circle, okay, under this circle, A and B dash are inverses. So B dash is the inverse of A with respect to omega. Okay, and this omega is called a standard unit circle because it is like the unit circle because the radius is 1 and standard because the center is at the origin. Okay, but so therefore, what it means, what is the interpretation of B? So B, which was the, I mean, when A was represented by the complex number Z, its inverse 1 by Z is represented by point B, where B is the conjugate of the inverse of A with respect to the standard unit circle. Okay. So from A, first if I take the inversion, from A I will get B dash, and then if I take the mirror image in the x-axis, I will get B, which is the 1 by Z vector. So basically, even inversion has a way of being represented in the complex number domain. Okay, so I mean, in this way, basically all the basic operations, addition, multiplication, all of those have nice geometric interpretation, and we can use that at the right moment as and how required. One another detail which I think I should cover. I don't know if this is formally done already, but do you know the complete definition of trigonometric functions? Like we know how to define sine theta and cos theta in a right angle triangle, but what if theta is greater than 90 degrees? Or if theta is negative, then how do you define sine and cos? So there is a 2D geometric like coordinate system definition of trigonometry. So I don't know if you are aware of that, but if not, then maybe just to give you the definition. So can you raise your hand if you already know this definition? Where you take the standard unit circle and any point on that. Okay, but looks like everybody is not aware of it. And then 2 or 3 people have raised their hand. Maybe I just quickly go over this. I don't want to dwell too much on this. So basically, if you have the coordinate system and any let theta be any real number, and generally speaking, I mean formally we should interpret theta in radians, but I'm taking some freedom that even if you want theta to be in degrees, that is fine for ease of understanding. So if consider the standard unit circle, which is at central origin and radius 1. So let's say the radius. Okay. So let theta be the standard unit circle. Okay. Then to find the trigonometric values of theta, that is sine theta and cos theta, the general procedure is you take the ray starting from O, basically construct a ray. Wait, let me use OP. Just that P lies on the standard unit circle and angle POX is equal to theta. Okay, so this angle is theta, and I mean as we generally allow theta to be any real number. I mean here I have noted P in the first quadrant, but that may not be the case. It could go to any of the quadrants. Like if theta is greater than 180 degrees, then it could come maybe somewhere over here, for example. So then this whole angle would be theta, for example, etc. And of course, after 360 degrees, the value starts to repeat. So that is why we call all of these functions as periodic. But I mean, for this definition, we can use a theta, which is like within 0 to 360. So then, if P has the coordinates x comma y, then we define sine of theta as y and cos theta is equal to x. Okay. So I mean, in this triangle whose hypotenuse is 1, of course, we see that if this has coordinates x comma y, then here we clearly see that cos theta will be x upon 1 and sin theta will be y upon 1. But what we are showing here is we are extending this definition to any angle theta. So in particular, if you take some theta greater than 90 degree, for example, okay, so let's say you take a theta around this 150 degrees, let's say. Now for this point, what is the x and y coordinate? So basically, you will see that in different quadrants, the sine and cos have a different sign. So in this quadrant, for example, the x coordinate is negative, but the y coordinate is still positive. Okay? So the sine of this angle will be positive, but cos of this angle will be negative, and things like that. Okay? So in general, through this definition, what we are able to say is that any point P on this standard unit circle, if it has a coordinates x comma y and this angle is theta, then basically I can write the coordinates of this point P as cos theta comma sin theta. Okay, and so this was for the standard unit circle. But if I draw any other standard circle, which means that a circle centered at O, but radius may not be 1 necessarily. Okay, so if I draw a larger circle like this, okay, let's say its radius is r. Then on this circle, again, any point which I take, if it is making an angle theta at the center, then that the coordinates of that point. So if I call it P2, so P2 will have coordinates r cos theta, comma r sin theta. And this directly ties to the polar coordinates which I was talking about last time. So basically this P2 can be written as x comma y. So where x and y are the Cartesian coordinates, or alternately I can denote it by these two values, that angle formed by the at the center and the distance from the origin. Okay, so therefore the other interpretation r angle theta, which is the polar version, can also be written. And if you know the Cartesian coordinates, if you know x comma y, you can figure out r and theta and vice versa. Okay, so we can interchange between them. So if you know r theta, then x comma y is simply r cos theta and r sin theta. But if you know x and y, what is the expression of r and theta will you write? So specifically, what is r in terms of x and y?
Sir, root x square plus y square.
Right? R is root x square plus y square, simple Pythagoras theorem. What about theta?
Cos inverse of x by r.
Okay, so theta you are writing as cos inverse of x by r. So that is almost correct. The problem is that this is some more advanced trigonometry that we have not yet covered. Cos inverse as a function, if you realize, I mean cos theta is itself periodic uh, with the way. Basically, when you take the inverse, you require a bijective function. If I draw the graph of cos theta, right? So let's say this is 0, proper axis. Okay, let us draw the graph of cos theta. Let's say on this axis, this is 90 degrees, 180, 270, 360. Okay, and this is 1. Then we all know that, I mean, the cos also looks like a sine wave. Basically, it starts at 1, it goes to 0. Okay, and from here it will repeat again. So when you take the cos inverse of any value, let's say you are talking about 1 by root 2, okay, maybe somewhere over here. So cos inverse means what is the value of theta such that cos theta is 1 by root. So on this graph, you will see that there is more than one point which has this property. This as well as this. So which of the two should you consider? Because both of them will have the same cos inverse. I mean, to show the same thing on the polar system, basically we are talking about these 2 points. If you take, let's take r equal to 1 for simplicity. Okay, so we are talking about a standard unit circle. Okay, but if you consider this vertical line such that this angle is 45 degrees and this angle is minus 45 degrees, then both this point and this point have the same value of cos. So we need some way to sort of disambiguate which of those we are talking about. Okay. So just saying theta is cos inverse x by r is not enough. Basically, we
And
have,
it should be sine inverse of y by r.
and it should be sine inverse of 1 by y by r. Okay. So I mean, yeah, I probably the definition which you are trying to say is you first find cos inverse x by r and then sine inverse y by r, and both of them will have two values, right? Which will be separated by like 180 degree or whatever. So then, which of the values of theta conform to both of them? That is the value you will use. Something like that.
Yes.
Sir, tan
Okay.
inverse of y by x.
Tan inverse of y by x. Okay. So let's draw the graph of tan, because it turns out tan is, in a way it is simpler, but the periodicity of tan is even more restricted, because tan, as you will know, has a period of only 180 degrees. So tan of 0, so if I minus 90 plus 90, so tan has a graph which looks something like this. At 0, tan is 0. At the at 180 degrees, at 90 degrees, there is no value of tan. So tan cannot be defined at the 90 and minus 90 points. But after that, it comes back, and this is how it behaves. Okay, so tan is helpful, but the problem is again that if you take two values on this on the graph which are opposite each other. Okay, so let's take a point here and here. You'll realize both the values of theta have the same value of tan, right? Because here, if it is cos theta and sin theta, here the values are minus cos theta and minus sin. So the ratio is exactly the same. So again, the ambiguity remains when you take tan inverse, which of the 2 points are you talking about? Okay, but in general, I would say tan is the easiest to sort of rewrite this definition. So the proper way to write is theta is equal to, first most important thing, what happens when you're talking about the origin? If your point is at the origin, right, you cannot define the angle theta at all, right? So in this whole time when you're writing x upon r, etc., what if the r is 0? Then this ratio will not have any meaning of at all. Okay, so theta is undefined if r equal to 0. That is the first thing that we have to be consciously aware of. Then suppose theta is, suppose r is not 0. Then what can we do? Then we can write theta is equal to tan inverse of y by x. But again, if you think about it, anytime I write anything in the denominator, I have to be careful. What if x is 0? So which means that I have to make that case separately also. That so if x is 0, now if x is 0, which means that our point is on the y-axis, right? So now in the y-axis, if it is on the positive side, then the angle is 90 degrees. So it is 90 degrees if x is 0 and y is positive, and it is minus 90 or 270 degrees if x is 0 and y less than 0. And maybe I could write this also in the same way, if x is 0 and y equal to 0. So now we have covered all the cases where the denominator could be 0. So now we are in a better position to write tan inverse y by x. But now, so this is where we have to make two conditions, make two cases. So this definition tan inverse y by x is perfectly valid in the upper half of the plane. Okay, so anywhere if your point is in this upper quadrant, that is fine, which means that basically if the y coordinate is greater than 0 or even equal to 0 is fine. And if your point is in the lower coordinate, lower half of the plane, like for example below the x-axis, then if you find tan inverse y by x, actually what you will get is simply this angle. Okay, but whereas what you're interested is in the full angle, so you have to add 180 to that. Okay, so therefore in this case it will be 180 degree plus tan inverse y by x if y less than. I hope I have covered all the cases. Even then, I'm concerned maybe the negative x-axis is not correctly covered here, but let it be. At least, this is the full technical definition of theta. In the if you want to write theta in terms of x and y, then you have to take care of all of these corner cases. Usually we don't bother with these details because it's understood from the context, but just so you be aware that what is the full technical detail. And in fact, there's a nice sort of corollary to this, which is used in programming often. So in programming, when you have tan inverse, right? So tan inverse is given as a function a tan, which takes a single value as input, right? That is the whatever was the value whose inverse you want to find. But many libraries implement another function called a tan 2, and a tan 2 takes two inputs. So it takes x comma y as input. So internally, this a tan 2 is going to be same as a tan. It will simply do the tan inverse of y by x. But in addition, this a tan 2 function will also add 180 degrees conditionally if it turns out that this y by x are in the second half of the quadrant. Okay. So it is like a tan inverse on its own is not enough many times to do the polar reverse coordinates. Okay. But yeah, and the point is basically you can convert back and forth between the Cartesian and the polar version of any given point. Okay, any details in this which are not clear? Okay. But these graphs of trigonometric functions are quite useful, and you should be aware of those. I think they will be covered quite formally in your future lectures. So in 10th or 11th standard, you will definitely do this topic in more detail, like graphs of the trigonometric functions, graphs of the inverse trigonometric functions, and things like that. I'm not going into those details right now because we have other priorities. But all of this is very important, like elementary ideas we should be aware of. Okay, so yeah, actually, just to complete the topic of complex numbers, another couple of things that we should point out that these are just notations, but we should be aware of this. So simply speaking, if your complex number z is given as a plus ib, then we call the real part of z, which is denoted by rez as a, and the imaginary part of z as b. So both this re and im, they are functions from complex numbers to real numbers. Okay, so all they are doing is like a projection. So they the re of z projects the complex number z onto the x-axis, and this imz projects the complex number onto the y-axis. And then the mod z is the distance of the z from the origin. So this is nothing but again the same r which we talked about. And the argument of z is the angle theta, which we have defined it here below in complex ways. So I will not go into that. But this a tan to a comma b, as I already introduced you to that, what that means. It is not a mathematical function, strictly speaking. It is a programming function, but will save us some effort to write the whole. Basically, whenever I write a tan to a comma b, there you should substitute this whole definition which I gave you, this whole undefined, and all of those conditions come up there. But the short form for all of that is this a tan function. Okay, so I think this completes the sort of technical introduction to complex numbers. Like all the basic operations now. So we can try to solve a few problems with this, like how we are trying to use this in geometry. So in particular, we started to do one problem last time. We will complete that one also. So that was on a triangle, you draw isosceles right angle triangles on all the sides, and you get a concurrency. Actually, I forgot. Generally, when I introduce complex number, there's a different problem I start with. That also has isosceles right angle triangle. That is why I got confused between those two problems. But the problem I really wanted to give you last time was this one. Okay. So we'll do this one first. Let me just write the problem first. Okay, so this is the diagram roughly. That ABCD is a quadrilateral whose diagonals are equal and perpendicular. Then on each side, I am drawing an isosceles right angle triangle. Okay, and these external vertices we are calling PQRS. Okay, then we have to prove that PR and QS are also equal and perpendicular. So yeah, that's what happened. I actually wanted to give you this problem last time, but because that one also had isosceles right angle triangle, so I got confused. But I mean, turns out even that problem can be done with complex numbers. Okay, we'll come back to that. But for now, we want to try and solve this problem. Okay, so one step in particular which I had mentioned last time, but I don't know if everybody followed the details, so I just want to repeat that is how. So when we assign, let's say we take some 2D coordinate plane in this 2D coordinate axis rather in this plane, and so we start to give complex coordinates to each point. And as I said, the convention is to use small letters to denote the complex coordinate. Okay. So let's say I want to find the complex coordinate of point P. So P in terms of ABCD. In particular, for finding the complex coordinate of P, it is enough to consider only A and B. Okay, so let me just draw that part of the diagram separately. So let's say you have this isosceles right angle triangle, okay, whose vertices are like this. Okay, then how do we find the complex coordinate of P in terms of A and B? So I had outlined the procedure last time, but I just want to repeat how that works. So the way it works is that suppose you have your XY coordinate axis may be somewhere else in the plane. Okay, the origin may not be located close to your diagram. But now what you can do, I want to translate this whole triangle to my origin. Okay, kind of a shift of origin. Okay, so I am interested in the same diagram, but which is drawn at my origin. So let's say I want something like this. Okay. So I just shifted this whole diagram over here. So in order to do that shift, so this is where the geometric interpretation starts to help you. and similarly OP dash will be equal and parallel to OP. Therefore, what we can say is that this triangle OP dash A dash is also an isosceles right angle triangle. Okay, and not only that, so can you tell me what is the coordinate of A dash, complex coordinate of A dash and P dash? In terms of A and B.
So A dash should be A minus B.
A dash will be A minus B, correct? And the reason for that is A is, I can say by the parallelogram law, OA vector is nothing but OA dash plus OB. Or if I write the same thing in complex numbers, it means that A is A dash plus B. Therefore, A dash is nothing but A minus B. Okay, and in the same way, P dash will be equal to P minus B. Okay, and now what is the relation between A dash and P dash in the red triangle? So in the red triangle, because this is an isosceles right angle triangle, therefore I know that OP dash, if I write everything in polar coordinates, if OA dash has some angle R and theta, and OP dash R1 theta on its side, OP dash has some angles R2 and theta 2. Then we know from the polar interpretation that basically the OP dash will have an argument of 45 degree plus angle OA dash. Okay, so OP dash, this angle theta 2 will be theta 1 plus 45 degrees, and the argument, the distance R2 from the origin will be 1 by root 2 times the distance of R1. Okay, in other words, basically from OA dash I can obtain OP dash by multiplying with the suitable complex number whose angle is 45 degrees and magnitude is 1 by root 2. Okay, so in polar domain, P dash is nothing but A dash times this complex number whose magnitude is 1 by root 2 and angle is 45 degrees. Okay, and so if I wanted to denote this in the normal Cartesian domain, this will be simply half plus half I. Okay, so in other words, P dash is A dash times half plus half I. Okay, and how do I obtain this half plus half I quickly? Basically, I can do the same operation. So this multiplication, which is taking OA dash into OP dash, I can do the same thing on the standard unit point. So which means that if I let me say this is the point 1 comma 0. Okay, then to this 1 comma 0, if I apply the same transformation, okay, rotation of 45 degrees and scaling by 1 by root 2. So I just have to observe where that point lands. So this 45 degree and this 1 by root 2 will land this point at half plus half I. You can check the geometry of this. Okay, so therefore P dash is A dash times half plus half I. And now instead of writing P dash A dash, so which was everything done for this translated version, I could do the same thing in the original triangle, which is APB, because I know the substitution of A dash and P dash. So if I substitute these details back, I'll get P minus B is equal to A minus B times Z. So I don't want to write this half plus half I every time, so I'm just calling it Z. Or if I take this to one side, basically I'm getting P is equal to B plus A minus B times Z. Finally. Okay, so this expression, which this time I sort of obtained formally through all the calculations, but informally you can quickly write this expression directly as I had done last time. So as I explained last time, if I just draw that triangle PAB again over here, This is the procedure that we are doing basically. Suppose wherever you are at the origin, I want to reach point P. So first step is I want to reach the point B first. Okay, so therefore I added plus B. Okay, then I took the vector BA. So vector BA is A minus B, and I need to rotate it and scale it down. So I need to rotate it with 45 degrees and scale it by 1 by root. And so that is this component Z, and that is how I reach point P. Okay, so this procedural way of thinking very easy because you can extend it. Like let's say from point P you want to go to point Q, you can continue this chain of reasoning. Okay, so that is how I can quickly write this expression without having to worry about all of these details. But I mean, I just thought you should know that what is happening at the back of the process. That actually what you're doing is you are translating the diagram to the origin. There you are performing the rotation and dilation, and then you are translating the diagram back to its original place. But all of that is happening under the hood. Okay, so I hope everybody understood this procedure, and I mean you can try practicing this by taking. So this was isosceles right angle triangle, but there is nothing special about that. Suppose I mean just to check if you have understood this idea. Suppose you have an equilateral triangle, and the points are something T, E, F. Okay, how will you write the coordinates of F in terms of T and E?
So D plus E minus D into K.
K, and what is K?
So theta is 60 and R is 1.
Correct. So K will be 1 angle 60 degrees, because basically we are looking at what is the spiral homothency around the point D, which will take E into it. In this case, because it's an equilateral triangle, there is only rotation, there is no dilation. Okay. So simply rotating through 60 degrees is sufficient. So K is 1 angle 60 degrees, or if you want to write it in the Cartesian domain, you just draw the same equilateral triangle on the unit points. Okay, so if this is 0 and this is 1, and you apply the same rotation, then where will 1 go? Okay, so what are the coordinates of this point? It will be half comma root 3 by 2, correct? So K can be also be written as half plus I times root 3 by 2. Okay, are you following this?
Yes, sir.
Okay, I mean, the more you use this in problems, the more comfortable you will get with this. If anybody is not able to follow the details. Okay. Okay, so this idea, if you understood, let us go back to the original problem and see what can we do there. So in this diagram, so if I apply this technique, I can get the coordinates of all the 4 points P, Q, R, S in terms of A, B, C, D, and then from there we want to try and important thing which is given to us, that AC equal to BD and AC is perpendicular to BD. This also we have to see if we can represent complex domain. So can you think of how I can interpret these two expressions, AC equal to BD and AC perpendicular to BD? What will that mean in terms of complex numbers? Okay, so if you see in this diagram, AC is this vector and BD is this vector. So roughly speaking, if I rotate AC by 90 degrees, I am getting the vector BD. Okay, so BD is AC rotated by 90 degrees. And I think, I mean, when we talk about vectors, I think everybody understands that the position in the plane does not matter. So, I mean, the fact that they don't share the origin or the head of the vector doesn't matter. So, this expression BD is AC rotated by 90 degrees. How can I write the same thing in complex numbers?
BD equal to AC into I or minus I.
Yeah, correct. So in this case, I think the rotation is counterclockwise, so it will be I. So this is D minus B is equal to C minus A times I. And why times I? Everybody understands that I is nothing but 0 plus 1 I, or in the polar domain, this is one angle 90 degrees. Okay. So multiplication by I is the same as rotation through 90 degrees. Okay, so you see how we have converted the given information into a purely complex number equation. Okay, d minus b equal to c minus a times I, and hopefully this should help us to solve the problem. So how do we get started? First, let us just write the complex coordinates of PQRS. So maybe I will use this. So every time I'm interested in z equal to half plus half I, which is that 1 by root 2 angle 45-degree rotation. Okay, so if I fix this as my z, then we know that p is nothing but b plus a minus b times z, and cyclically I could write all the three of them. And actually, that is one power of this complex number. I don't even have to do the diagram to confirm what I'm writing, but by simply the symmetry and cyclicity of ABCD, I can just write all of those expressions just like that. Okay. And now the question is asking us to deduce something about PR and QS. Okay. So from this, I can figure out what are the expressions of PR and QS. Okay. So the vector PR, which will be R minus P, and vector QS will be equal to S minus Q. Okay. So what will I get? Okay, so this is what I'm getting for PR and QS. What do you suggest we can do now? Because always keep in mind the information we want to use is this, the d minus b equal to c minus a times I. So this should always be at the back of our mind that I want to use this somehow. So do you see I can rearrange the brackets and put everything in terms of d minus b and c minus a. So this second bracket in each case can also be factored out such that, I mean, I can see d minus b is common. So I can continue to write this as PR is equal to, I can take d minus b in one bracket and inside what will I get? 1 minus z plus z times c minus. And similarly QS, what can I write QS as? Again, I could write it as d minus b times z and plus c minus a times, I guess, z minus 1.
Yes, sir.
And now here, anytime you see an opportunity to eliminate variables, we should take that. So in particular, because we know this expression, so everywhere we have d minus b, we can substitute it with I times c minus b. So then if we do that, are you able to see that we can finish this problem now?
Yes, sir.
Okay, so PR will be nothing but, so now c minus a will come out common out of the whole thing, and inside I will have simply I times 1 minus z plus z, and QS similarly it will be c minus a times I times z plus z minus. And now here z is a constant, z is a value I know, it is equal to half plus half I. So I can multiply and confirm that what am I getting into. So PR turns out to be c minus a times So whether here you will observe z is equal to this, then 1 minus z is actually the conjugate of z. Okay. So 1 minus z turns out to be the conjugate of z. But anyway, that doesn't matter here. Okay, so the first bracket 1 minus z, which is half minus half I. If I multiply with I get half I minus minus is 1. And QS is C minus 8 times. But unfortunately, this tablet is vertical. If I were teaching in the class, I would have the advantage of writing everything horizontally. So I don't have to keep writing PR, QS alternately this way. But anyway, I will work with what we have. Okay, so again, now if I combine the real and imaginary parts, so this is half, so this is 1 plus I, and QS is C minus 8 times. Minus 1 plus I. Okay, so these are the values I'm getting, 1 plus I and minus 1 plus I. And you can check that these two numbers on the coordinate plane, 1 plus I, if 1 plus I is located over here, and minus 1 plus I is located over here. So they are both equal in magnitude, and the angle between them is 90 degrees. So therefore, PR equal to QS, and PR is perpendicular. Okay. I mean, because this is the first time we are applying complex numbers, so we wrote a lot of details fully. But in reality, when we are doing the problem, a lot of things can be done much quicker. But I hope you got the general idea that how you can use complex numbers to represent information. I mean, the most important sort of hint that which problem you should try to use complex numbers is when you have this kind of symmetry that you have multiple triangles of the same size and shape, which means that the fact that the same spiral similarity Z was applicable in each case was useful, because then that Z could come out as common and a lot of things could be simplified. Okay, so that is the hint that you can look for, that whenever you have this opportunity to simplify the same spiral similarity in multiple places, you can try to use complex numbers. Okay. By the way, does anybody know how to do this problem with using pure geometry? In case anybody has seen this problem before, do you know how to do this with pure geometry? I used to know, I've forgotten the proof. It involves somehow through parallelograms, you have to sort of cut and paste the diagram. The problem here is this PR and QS. I have to show that they are 90 degrees and they are equal in length, but they don't have any vertex in common. So somehow I have to introduce the vertex which is common to both of them. And then, I mean, in some way, let's say I translate both of them to have a common starting point. Okay. So then let's say these are my two vectors then it's enough to show that they are forming an isosceles right angle triangle, because then that will mean that the original two lines also have the same length and perpendicular to each other. Okay. So I think I'm forgetting where we have to translate them. Probably I'll encourage you to try this. Try to put both of them at the starting with starting A, for example. Okay. So basically, I want to construct a parallelogram ASQ something Q dash, let's say. And similarly, I want to construct a parallelogram APR R dash, for example, something like this. Something like this. So then now what will happen that these two new lines, it's enough to show that these two are perpendicular and equal in length, because then that will mean the original two lines are also having the same relation. But how to achieve that, I'm forgetting now. But it can be done. It's kind of, I would say this is definitely a problem where the complex number approach has some distinct advantage. Okay, it is much simpler to visualize. It doesn't have require any special construction like this. Okay, let's do one more problem using complex numbers, and then we'll go to barycentric coordinates in more detail. Because that is like definitely the theory of the triangle where all of those things come to more useful point. So this second problem is probably we all know how to do this using pure geometry, but take this. Okay, I don't know how to write this properly, but anyway, probably it's easier to draw the diagram. Okay, so suppose you construct a square like this. So it turns out this triangle ABC and triangle AQS, they have lots of interesting connection with each other. In particular, what we want to prove here is the median of triangle AQS, right? So if I take the median and the altitude of triangle ABC, they are the same line. So I want to prove that these 3 points basically are collinear. If I call this the foot of the altitude as D over here, and the midpoint of QS as M, that I want to prove that DAM they are collinear. And the reverse also happens, that if I take the altitude over here, that will be the median over here. Does anybody already know this property through pure geometry? Can you raise your hand? Okay. Okay, so we can do this with pure geometry also, and it's not that difficult also, by the way. But again, I just want to show quickly how even complex number has a very nice and kind of quick solution which is useful here. So this is what we can do in complex number. Let's, I don't think it is necessary, but because it might simplify the calculation, let me take A as my origin. Okay. So I'll put my origin at A. Okay. And then the coordinates of B will be small b at small c. Okay. Then what will be the coordinates of S and Q?
S will be IC
S will be IC. And what about Q?
minus IB.
Minus IB. And now M is the mid, let's say M is the midpoint of SQ. Then what will the coordinate of MP?
minus IB plus IC by 2.
Right? So do you see directly why OM will be perpendicular to BC? Because the vector BC is C minus B. And this is nothing but I times, half into I times that. Okay, so do you see that OM vector is nothing but vector BC, which is C minus B into half into I. And clearly multiplying by half doesn't change the angle. It will only increase or decrease the length. But multiplying by I will rotate it by 90 degrees. So therefore, what it means, so in fact, this gives you additional information, which I don't know if the pure geometry solution gave. That not only is OM is perpendicular to BC, but OM is also half of BC in length. Okay, are you able to follow this?
Yes, sir.
Okay, so a very quick solution directly gives you what you want. Okay, there are some other interesting properties in this diagram also, which I'll just indicate. We will not do them in full, but turns out, because if you think about these two triangles, ABC and ASQ, they have the same angle bisector, right? If I take the internal angle bisector, you will realize that they will have the same bisector, because this 90 degrees is like we are going 90 degrees in both directions symmetrically. So they will both have the same angle bisector. So what is the implication of this? When you reflect a line, let's say you take this red line, okay, which this red line is the altitude in the lower triangle and it is the median in the upper triangle. And if you reflect it in this angle bisector line, in the lower triangle, it will go to a new position where we already know that if I consider the circumcenter as O, then AO and AD are isogonal conjugates, which means that they have the same angle with respect to this center line. But if we do this reflection, then the line above this OM goes into what is called a symmedian. So symmedian is the isogonal conjugate of the median. Okay. So the conclusion is that just as the median in the upper triangle, so median in the upper triangle is the same as the altitude in the lower triangle. Then similarly the symmedian in the upper triangle is the same as the line AO. The line joining the vertex to the circumcenter in the lower triangle. And all of this happens because the bisector is exactly the same. So both of them have the same angle bisector, both internal and external values. Even the external angle bisector will be the same because that is nothing but the internal bisector rotated by 90 degrees. Okay. And in fact, this configuration goes even further than that. So here I just drew the squares on two sides. In fact, I can draw the squares on all the three sides. Okay. So I just denote it over here, and I'll get a configuration like this. So now, if you look at these three triangles together, okay, these three new external triangles. So it turns out that because the median of the upper triangle is AM is the altitude of the original triangle ABC, which means that if I take the individual medians of each of these three triangles, right? So if I, let's say, take the midpoints of each of these sides, LM and let's say, then I have a concurrency here that AM, BL and CN are concurrent, and that is obvious because each of them is the altitude of the inner triangle. So in fact, the point where these three lines will meet is the orthocenter of triangle ABC. And so, in fact, not only this, there are several other concurrencies associated with this, which will also come up. In particular, what you can do, right? You can take the let me just free up some space over here. So you can apply a translation to each of these three triangles. If I draw the altitudes, so in the same way, if I draw the altitudes of the three triangles, they will be concurrent at the inside, because in each case the altitude of the upper triangle is the median of the original triangle ABC. So in fact, the three altitudes like this will be concurrent at the centroid of the original triangle. But not only that, if I translate these triangles, so if I apply a vector translation of AG on the first triangle, I'll get a triangle like this. Okay, so this original upper triangle has been translated into this new position. And I could do the same thing with the remaining two triangles also. With BG and CG as my vectors of translation, I'll get a completely new diagram. So almost like a jigsaw puzzle, I can assemble these three side triangles into one new triangle in the middle. Okay. And there are some further properties that this new triangle, now I'm forgetting the details. There is a lot more complexity, but I mean, so you can try to figure out what is the relation of this new triangle with the original triangle ABC. Like if you know this new triangle, you can construct the original triangle and vice versa. Things like that. Okay, but anyway, I mean, there are a lot of possibilities here. Not, of course, not all of this requires you to do with complex numbers. You can do most of these things with pure geometry also. But it's a nice configuration. Okay, so then with these couple of examples, I want to move to barycentric coordinates once more. So I briefly mentioned what barycentric coordinates are, but now let us do it a bit more formally. Okay, so basically it is a system which allows us to assign coordinates to every point in the plane and with reference to a given triangle. Okay, so suppose you have a triangle ABC and you take any point P. Okay. Now, if I consider this line AP, let it meet the opposite side at some point D. Then we all know that the ratio BD is upon DC will be equal to the ratio of these two areas. Is that fine?
Yes, sir.
Okay. Now in the complex numbers, if we assign small letters to each of these points A, B, C, E, and D, then we have basically a section formula of kinds on this line BDC. So I can write D as equal to. So if I know this ratio, right, BD upon DC, if I call this, I can directly write. So D will be given by cross multiplication. So B times the ratio in the denominator. So PCA plus C times PAB. Okay, so I'm just using a section formula in complex domain. So that is how I obtained the coordinate of point D. And from there now I can reach point P also, because I know the ratio AP upon PD in the same way. So what can I write for ratio of AP upon PD? And in particular, I want to express everything in terms of these three fundamental values. So PAB, PBCA, and PCA. So the areas of these three triangles are what matter to me. Then how can I write AP upon PD?
So area of APB plus BD upon BC into area of PBC.
I couldn't hear you properly, but I think what you're doing is, if the idea is correct. So basically, I have two triangles over here on the left side of AD. Okay, so the area of APB upon PBD. So by normal geometry that we know, this will be equal to PAB upon PBD. Okay, so the ratio of these two first triangles on the left side, and it will also be equal to the similar two triangles on the right side. Okay, and then I can apply theorem of equal ratios to add these two together. Is that what you did? And on the denominator will be PBD plus PDC, which is simply PBC. Okay, so now I know, if I know again, I know the coordinates of point D, and on AP upon PD, I can apply sectional formula once more, and I'll get the coordinates of capital P. Okay, so capital P, the coordinate will be small p is equal to, again, A times PBC plus D times sum of all of them. Okay, I hope you are following how I'm applying section formula every time. It is simply cross multiplication, right? So in this ratio AP upon PD, the coordinate of A will be multiplied by the weight on the denominator. So that is why A is being multiplied by PBC, and the coordinate of D will be multiplied by the numerator. So that's why D is being multiplied by PAB plus PC.
Yes, sir.
And now here I'll substitute this, and you'll see the denominator gets cancelled. This PAB plus PCB plus PCA, this and this will get cancelled. And therefore, what I'll ultimately will be left with is P is nothing but A times PBC plus B times PCA plus C times PAB upon, so sum of all of these nothing but the area of the triangle ABC. Okay. And now if I just split this is A times PBC upon ABC plus B times PCA upon ABC plus C times PAB upon. Okay. So these variables, which I'll call them as alpha, beta, and gamma. Okay. So this triple of values alpha, beta, gamma is what I call the barycentric coordinate of point P, and they satisfy the condition that alpha plus beta plus gamma equal to 1. Okay. So basically in a given triangle, if you have any point P, and I know I can find the areas of these three triangles. Okay. So if I call them alpha, beta, gamma, or technically it is alpha upon delta, beta upon delta, gamma upon delta, where delta is ABC. Okay, then I can find out the barycentric coordinates of point. So it's a useful idea to visualize how the barycentric coordinates change when the point P moves around in the plane. And most importantly, there is no reason for point P to be inside the triangle. Okay, because all of these are directed areas. So the ratio PBC upon ABC means that if both of them are counterclockwise, then the ratio is positive. But what happens? Let's say if I take the point P over here, below the line BC, then you realize that PBC and ABC don't have the same orientation anymore. If PBC is
Will
clockwise,
become
ABC
negative.
then alpha will become negative. Correct?
Yes, sir.
But in all cases, basically alpha, beta, gamma can be any real numbers as long as they satisfy this condition that their sum is equal to 1. So like there is a one-to-one correspondence between all the points in the plane and all the triplets alpha, beta, gamma whose sum is 1. So
Sir,
yeah, go ahead.
so shouldn't it be alpha times delta instead of alpha upon delta?
Oh yes, you are correct. Yeah. So the area of these are alpha delta, beta delta, and gamma delta. Okay, so let's just try to find out the barycentric coordinates of the few special points that we know in the triangle. So, for example, I think we already started with this last time. So the coordinates of the three vertices themselves. So A is nothing but 1, 0, 0, B 0, 1, 0, and C 0, 0, 1. Okay, does everybody see that? Because basically, in fact, any point on the line BC, you'll realize that its alpha coordinate will be 0 because area of PBC is 0, correct? So any point on line BC, alpha will equal to 0. And same will go for the other three. In fact, there is a even broader condition that you can derive. Any line in the plane, so any line, just as we can talk about equation of a line in a 2D coordinate system, in the same way, this is also a perfectly valid coordinate system. So every point in the plane has a coordinate, alpha, beta, gamma. So you can talk about the equation of a line. So any line L in the plane has an equation of the form some alpha times h plus beta times k plus gamma times L equal to 0 for some h comma k comma L real numbers. Okay. For example, for the line BC, it just happens to be the case that h is equal to 1 and k and L are equal to 0. But in general, any line you can draw will have an equation of this type, and you can try to derive that also. That how will be that equation look like? In particular, there is a very interesting thing which is going to happen here. I mean, this could be true for any values of HKL, but in particular, you see, if I multiply an equation like this with some constant, the equation will still remain true. So I can choose HKL such that H plus K plus L equal to 1. Okay, so I can impose this additional constraint without any problem at all. And now what is happening? See, HKL themselves are triplet. So there is a kind of duality happening that every point in the plane has a coordinate and every line also has a coordinate. So the same triplet HKL represents some point in the plane as well as a line. So in a way, even the line has a three component coordinate and the point also has a 3 component coordinate. So there is a kind of a duality which happens. So just as if you remember, we had done the topic of poles and polars. which had set up a one-to-one bijection between all the points in the plane and all the lines in the plane. In the same way, here you have set up a one-to-one bijection between all the points and the lines once more. So you will see a lot of similarity between that whole theory of poles and polars and this one. Okay. In particular, turns out that one key idea of poles and polars was the concurrency and collinearity. That under this correspondence, if some points A, B, C are collinear, then their corresponding lines are concurrent. And so those kinds of things happen here also. And all of this is not hard to prove, by the way. It is just a lot of algebra and calculations. They are all linear calculations. There is no quadratic or anything. Just perfect linear algebra which yields all of these properties. But it is useful to have all of this context in mind, that how something that we have done in a completely different topic like poles and polars has connections over here also. So in a way, in fact, you can call this line as the polar of point P with respect to the triangle ABC. So now we are taking poles and polar with respect to a triangle. The last time we had taken poles and polar with respect to a circle. So I mean, it's a completely different domain now, but still there is a lot of validity. And so in fact, under this mapping, you will see that because the point A has the coordinate 1, 0, 0, and the line BC has the coordinate 1, 0, 0. So point A and point BC, line BC are the poles and polars of each other with respect to the triangle ABC. And I mean, a lot of the interesting things happen like that. Okay, but anyway, so I want to focus our attention on some of the special points in the plane, like the centroid, orthocenter, circumcenter, and what are their barycentric coordinates. Okay. So what about the centroid, for example? I think we've already done this. So centroid G, what are its barycentric coordinates?
1/3, 1/3, 1/3.
Correct. Because all the three triangles have the same area, PAB, PBC, and PCA. What about the incenter?
Sir, in center will be A by 2s, B by 2s, C by 2s.
Yeah, correct. Because
Yes, sir.
the
A by
areas of the three triangles, they all have the same height, which is small r. So the ratio will be simply the length of the sides, right? There is one small point. See, every time because we want to ensure that the sum is one, therefore we have to put the appropriate denominator common. There is a what we can call generalized paracentric coordinates, and I mean this is formally studied. It is not something which I am introducing, but I mean in the generalized paracentric coordinates, right? Alpha, beta, gamma don't need to satisfy the sum equal to one property. But in that case, the way they write the coordinates, so if the point P has the coordinates alpha, beta, gamma, then in the complex number, the coordinate of P is written as A alpha plus B beta plus C gamma upon alpha plus beta plus gamma. So they just normalize it that way. So I mean, in a way, it takes away the effort of normalizing every time. In this sort of generalized coordinate system, you could simply write centroid as 1 comma 1 comma 1, for example, and in center will be simply A comma B comma C. Okay, but I mean we have to be careful which system we are talking about. We should not like interchange at a halfway point between this other system. Okay, so for now, let's not talk about this generalized paracentric coordinates, but just keep that in mind that if you want, you can use this generalized system in some cases. Okay, so this is the incenter. What about the excenters? Let's say the excenter opposite A. So I1.
Sir, in generalized form, that also will be ABC.
But because I1 lies outside the triangle, won't some of the signs change?
so minus A by 2 into S minus A, B by 2 into S minus A, and C by 2 into S minus A.
Right. So in the generalized system, it will be simply minus A, B, and C. But since we want to normalize, we'll divide by B plus C minus A every time, right? So B plus C minus A is nothing but twice of S minus A. Okay, does everybody agree? Okay, now, and we can find a few more points. Okay, let's just do one more point, the circumcenter. Correct. Is this calculation correct? The excenter, I hope I have divided with the correct ratio. Seems correct to me at least. So for circumcenter, you realize that the base for the three triangles are ABC, and the altitudes are basically r cos A, r cos B, and r cos C. Is that correct? So this altitude, let's say for the first triangle, OBC. So the area of triangle OBC will be half into A into r cos A. And so one way you can simplify this, if I substitute A, small a as 2r sin A by sine rule, then this will be simply r square into sine A into cos. Or I could write it as r square by 2 into sine of 2a, because sine of 2a is 2 sine a cos a. Okay. And then if I do the same thing for all the three sides, basically this r square by 2 will be a common factor, so it will cancel out. So in terms of generalized coordinates, the circumcenter is simply sine of 2a, sine of 2b, sine of 2c. But to normalize, I divide every time with sigma sine 2a. Okay, is everybody following this?
So can you repeat?
Yes. So basically, we want to find the area of triangle OBC. The base is small a and the height this one. So in the original triangle, this angle is A. So the center angle BOC is twice A. So which means that each of these half angle is again A. And the length OB is capital R. So therefore, in this triangle, I can find the altitude, which is simply R cos A. Correct?
Yes, sir.
Okay. So then therefore, the area of the triangle is simply half into A into R cos A. And now the small a by sine rule, what is sine rule? A by sine A is equal to B by sine B equal to C by sine C equal to 2R. In other words, which means that small a is 2R times sine B. So I can do that substitution over here. So I'll get R square sine A into cos A. Now I'm dividing and multiplying by 2. Okay. So I get 2 sine A cos A, which is a double angle formula, which is equal to sine of 2A. In case you don't know this, you will study this formula later on. Okay. For now, you can just take it as it is, that sine of 2A is 2 sine A cos A. Therefore, the area of the triangle OBC is r square by 2 into sine of 2A. And the r square by 2 will factor out as common from all the three triangles in the same way. So ultimately, the barycentric coordinates, the generalized barycentric coordinate are simply sine 2a, comma sine 2b, comma sine 2c. But to normalize the sum to 1, therefore I divide the whole thing by sigma sine 2a.
Okay, sir, understood.
Sir, by Heron's formula, it will be a root 4r square minus a square, comma b root 4r square minus b square, and c root 4r square minus c square.
I think we need to check if that and this answer is the same. It should be the same because both methods are valid. But yeah, that's a good point. So, and here I guess the values are given in terms of sine of the angles. If you are interested to find a formula which talks about the in terms of the lengths, the segments, then you can use for Heron's formula. Can you just tell me the expression which you finally mentioned?
Sir, a root 4r square minus a square.
4r square minus a square. Okay, and
Actually, it is, sir, it is a by 4, but in generalized form by 4.
Okay. A root 4r square minus a square. That's interesting. Okay. So by the way, I mean the point of finding all of these values was not only just to give practice, but we are going to see some further connections very soon. In particular, I wanted to notice something about the incenter and the excenter, I and I1. If you look at these values, right, particularly look at the second and third coordinate, that is the beta and gamma. Do you see they are in the same ratio? So the ratio B is to C is satisfied by both coordinates. So if you think about it, that is true for every point on the angle bisector. So if I consider the angle bisector of ABC, okay, you'll realize that every point on this line, no matter where I take it, if I drop the altitudes, and basically if this point has the coordinates alpha comma beta comma gamma, then the ratio of beta is to gamma will be always b is to c. Do you see that why that is the case? Because the ratio beta is to gamma is nothing but the ratio of the areas of these two triangles. Beta is to gamma is nothing but the ratio of the areas of PCA and PAB. And since it is on the angle bisector, the height is always going to be equal. Therefore, this is nothing but the ratio of the bases. Is that fine?
Yes, sir.
Okay. And the important point is this can be used as an if and only if thing. So if I know that a point lies on this angle bisector, then its ratio is b to c. Conversely, if I know that some point has the barycentric coordinates such that beta is to gamma equal to b and c, I can say that that lies on this line. Okay, in other words, this line, just as we were talking about the equations of the line, so this line in particular has the equation beta. How is the right equation for this?
Sir, beta is gamma into constant.
Sorry, can you repeat that?
Sir, beta is gamma into constant.
Yeah, constant, but that constant is b upon c, right? So I mean, I'm trying to write it in the normalized form, like a alpha times something plus beta times something, that form. So alpha has the coefficient 0, so 0 times alpha plus what should I multiply beta with? Beta upon gamma is b upon c. So beta into c equal to b into gamma. So I can, for example, I could write the equation like this. Okay, 0 alpha plus c times beta minus b times gamma equal to 0. So this is the equation of the angle bisector. Okay, so the same if and only if thing happens that any point lies on the angle bisector, it is going to satisfy this equation, and any point which satisfies this equation is going to lie on that angle bisector. Okay, is everybody following that? And the important thing is that any line passing through A will have some constant. So yeah, actually what you said beta upon gamma is constant. That is true for any line passing through A. So if I take any other line, and finally what matters here, the ratio of the altitudes was 1. In some other case it may not be 1, but whatever it is going to be constant, right? So if I take any other line passing through A, again the ratio of the two barycentric coordinate, the second and third coordinate, will always be constant along this line. Okay. So basically, any line passing through A will has the equation beta upon gamma is some constant k. Okay. The value of the k will change depending on which line you are talking about, but the equation will always be like this. Does everybody follow this?
Yes, sir.
Okay. So if we understand this, let's go back to the problem which I gave you last time by mistake. So the triangle ABC, and I know there are simpler proofs, but I just want to demonstrate how this observation allows us to do that problem once more with barycentric coordinates. So we had constructed the isosceles right angle triangle on all the three sides, and we want to show that these AP, BQ, C are concurrent. Okay, so all I want to do now is find the barycentric coordinates of point P. And in particular, I am only interested in the beta and gamma. I don't even care about alpha. So if or other I would say if P has the barycentric coordinate alpha, beta, gamma, then I want us to find what is the ratio of beta is to gamma. Okay, so for that I'm interested in the so beta is to gamma is nothing but the ratio of the triangle PCA upon PAB. Oh, no, this is difficult. I want to zoom out, but at the same time, and this is such a narrow working space. Just draw the diagram. I made a mistake in drawing it like that. Okay, so I am only going to draw the side. I don't care about the other two triangles for now. So I am only going to draw the isosceles right angle triangle on one side, and I am interested in the ratio beta is to gamma, which is nothing but the ratio of the areas PCA upon PAB. Okay, for that, what I can do if I drop the altitudes from P to the two sides, then I can write this is nothing but so half will go common. So this is nothing but the side B into the this first altitude H1 and H2 if I call them. So B into H1 upon C into H2. And now this H1, H2 themselves I can write in terms of trigonometry. So here this angle is C plus 45 and this angle is so this is B plus 45. So this angle is actually 180 minus B minus 45. Okay, but as it turns out, the sine is supplementary. The sine of supplementary angles is equal. So sine of this angle will be same as sine of B plus 45. Okay. So therefore, this simply turns out to be B times. And by the way, the hypotenuse in both cases, which is PC and PB, they are equal in length. So I don't have to write that also. So I can directly write H1 is simply sine of C plus 45 and H2 is sine of B plus 40. Okay, is everybody following these calculations?
Yes.
Okay, and now here is the sort of you can say ingenious stroke that which finishes this problem just like that. In one line, the problem will be finished now. What I'll do, I can rearrange these coordinates. So this is the ratio of beta is to gamma, remember. I'll write this as B upon sine B plus 45 upon C upon sine C plus 40. So it is the same expression, but I separated the B and C now. So how does this help us? The problem is almost over now if you just observe something carefully. So remember, this is the ratio of the barycentric coordinates beta and gamma of point P. But from what we said earlier, any point on this line AP will have the same ratio of beta is to gamma, correct?
Yes.
So now suppose there is a point in the plane S, I don't know where it is, but suppose that point S has the and so this is generalized coordinate, but let's say because I don't want to go into generalized coordinate now, so let me just divide all of them with the sigma of the three numerator. Okay, so sigma A upon sin 45. So I'm just sort of dividing by the same constant so that the sum of these is equal to 1. Okay, so if so these three are real numbers whose sum is 1. So there exists some point in the plane whose barycentric coordinates is given by this triplet. And if you observe, this point S has the same beta is to gamma ratio as my point P. Therefore, what I can say is that this point S has to lie on line AP. But by symmetry, the same thing will be applicable for the remaining two Savians also. So S, so this point S, which has this barycentric coordinates, S belongs to line AP because the ratio beta is to gamma is the same for this. But similarly, this calculation which I did over here to find the beta upon gamma ratio for P, I could repeat the same calculation for the points Q and R also. And what I'll say is that I'll get S has to lie on BQ and CR also. In the case of BQ, the ratio which will matter is gamma is to alpha, and in the case of CR, the ratio will be alpha is to beta. Therefore, I found the point in the plane which lies on all the three lines. Therefore, the three lines are concurrent. Okay, and all of this happened only because I could separate this B and C this way. So therefore, the cyclicity or the symmetry could be applied. Okay, so this separation of concerns, you can say in a way that I'm separating the concerns of beta and gamma, or rather side B and side C. That is what allowed us to finish this problem. Okay, does everybody follow this argument? What I did in the last few steps, or you want me to repeat any part? Okay, the key idea was to make this jump that once you see that P has the ratio beta and gamma, which is given by this B by sin 45, C by sin 45. Therefore, you directly consider this point S in the plane whose generalized coordinates are A by sin 45, B by sin 45, C by sin 45. And like specific barycentric coordinates, you have to divide by the sum of these three values. Okay, so it is guaranteed that such a point exists in the plane. And then it is also guaranteed that that point will lie on line AP because the beta and gamma are in the same ratio. And it doesn't take much to see that here the value of 45 was completely irrelevant. If you replace 45 with any angle theta, this whole argument is still true. And I think we already know that from normal trigonometric for theorem, rather trigonometric proof of this property, that 45 degrees could be replaced by any angle. But are you able to follow the logic now? Why this can be done through complex numbers also?
Yes, sir.
Okay, so then there are a lot of interesting things which happen in complex numbers. Let me show just one more nice thing. So this has to do with isogonal conjugate. So can you raise your hand if you remember what is isogonal conjugate? So I hope this has been taught to you. I think I haven't been taught to you, but anyway, maybe I missed to do that. So basically, it is if I have any point in the plane on triangle ABC, okay. So I can consider the reflection of AP in the angle bisector. So this is the angle bisector of angle BAC. Then I could consider the reflection of this AP. In the same way, I could consider the reflection of BP also. and CP also. So these original lines AP, BP, CP were concurrent. These what are called isogonal reflections, they are also concurrent. So if AP, if BP, CP are concurrent, that's not a very nice way of saying that. I mean, okay, I'll just put it in a different way. Let AP be reflected in the angle bisectors of angle A, angle B, respectively, to get PQ1, PQ2, CQ3. Okay. So these reflected rays are also concurrent. Can you see why that is going to be true? Which property will directly say that this is true? So how about trigonometric version of Cheva's theorem? Okay. So what is trigonometric Cheva's theorem? It has to do with the ratios of the sines of the angles. So normal Cheva's theorem deals with the ratios of the sides, the opposite segment. So if I extend AP to meet the line DC, then the ratio BD upon DC and all of those are that product is equal to 1. That is Cheva's theorem. But what this is trigonometric version of Cheva's theorem. So I think we have done this, but maybe you need to revise. Which deals with the angles. So sine alpha 1 upon sine alpha 2. So if you remember that the ratio BD upon DC can be written as BA upon AC into sine of alpha 1 upon sine alpha 2. You remember this?
Yes, sir.
In case you have forgotten this, you need to go back and watch those lectures. So I think we have covered all of this in the cross ratio topic. Almost the first 2 or 3 topics that we did, we had done this. Okay, so when we do this cyclically, the Cheva's theorem, which is the product BD into DC, everything, this BA upon AC, this product gets cancelled out of everything. And so what you're left with is purely the ratio of the sine. Okay, so trigonometric Cheva's theorem says that this AP, BP, CP are concurrent. If they are concurrent, then sine of alpha 1 upon sine of alpha 2, sine of beta 1 upon sine beta 2, this product is equal to 1, and vice versa. So the converse is also true, that if you have 3 line segments or rays whose this product of this sine is equal to 1, then those 3 rays are going to be concurrent. Now what is happening here in isogonal conjugate is that when I take the reflection in the angle bisector, right? So basically alpha 1 and alpha 2 get reversed, right? So in originally this is alpha 1 and this is alpha 2. For the reflected ray, this is alpha 2 and this is alpha 1. So now if I try to apply Cheva's theorem, trigonometric Cheva's theorem, the product will be still equal to 1 because everything will be reciprocal. All the 3 terms will be reciprocal in the same way. Okay. So therefore, if the original 3 rays AP, BP, CP are concurrent, then the reflections AQ, BQ, CQ, they are also concurrent. Okay. So therefore, this point P and Q are called the isogonal conjugates of each other. Isogonal conjugates. Okay. And this is like a reflexive operation because starting from P, you will construct its isogonal conjugate, you will get Q. If you start from Q, you will come back to P. Okay, so P and Q are each other's isogonal conjugate. Okay, we are almost out of time. So I want you to cover everything, but this is the homework for you. Try to figure out, answer this question. Does each point in the plane have an isogonal conjugate? Okay. Are there some points in the plane which don't have isogonal conjugate at all? That may be a very strange question, but if you try to think about it, you will realize what it means. Okay. And we'll try to answer this question through pure geometry as well as through complex numbers, and that will give us new proofs of some properties which you already know. But I won't reveal what properties because that will give away the hint. But there exists a set which does not have any isogonal conjugate. So we try to discover what is that set of points on the plane. Okay, I think we are almost done for today. Let me just try to think if there is any other homework which I can give you. Yeah, actually, one more homework which you can try to do is, so we went back and we found the barycentric coordinates of G and O. So I would encourage you to try and find the barycentric coordinate of H also. So find the barycentric coordinate of H and then prove through complex numbers that OGH are collinear. Okay. So what is that condition going to look like when are 3 points collinear? So what does that mean in terms of the barycentric coordinates? That is something that we'll do next time, and we'll see that OGH are really collinear that way. And in the same way, the midpoint of I and I1, right? So in the standard configuration, we know that I and I1. What is the midpoint of I and I1? Where does that point lie?
Sir, on the circumcircle.
Sir, on the circumcircle.
So because you know the barycentric coordinates of I and I1, you can also figure out the barycentric coordinates of this point L. So just do that as a preparation for, I mean, we'll do this next time, but you can just try to prepare for this and check that is OL perpendicular to BC, for example. So all of these things we know from pure geometry, but I just want you to rediscover it from complex number perspective. Okay, I think that's all for today. Thank you. Bye.
Thank you so
Thank
much.
you, sir.